Welcome to the second video presenting MOF4AIR main concepts. After looking at what are MOFs, we will now be looking at how we can use them as solvents for carbon capture. I'm Richard Blom from SINTEF, and I'll be walking you through this video. The global carbon cycle was balanced through millions of years, until human activity started to add significant amount of CO2 in the atmosphere around a decade ago as part of the global industrialization. The increased CO2 level led to an abrupt increase in the average temperature of the Earth, indicated by the hockey-shaped curve of the average global temperature over the last 2,000 years. CO2 capture and storage, CCS, are technologies where CO2 is removed from industrial exhaust gases or directly from air, so-called DUC. Most of the CO2 should be stored permanently underground, while a limited amount of CO2 also can be used as a raw material, as a carbon source for materials and fuels. One way to capture CO2 is to use solid adsorbents. In the following, I will tell you why this is a viable route and why we believe metal organic frameworks, MOFs, can play a role in the development of adsorbent-based CO2 capture technologies. Compared to state-of-the-art technologies for CO2 capture based on amine solutions, adsorbent-based separation technologies may require lower regeneration energy, which in most cases give lower operational cost of the CO2 capture plant. In addition, since most solid adsorbents are stable at the process conditions used, negligible environmental footprint is expected, opposed to the amine solution process, for which a large amount of waste is a challenge. The main families of solid adsorbents are activated carbons, zeolites, amine-grafted silicas, and MOFs. We believe MOFs form the most promising class of adsorbents, since they can be tailor-made to have high CO2 capacities, intermediate CO2 absorption energies, and high selectivity to CO2 over other components in flue gases, such as nitrogen. Many MOFs can also work well in the presence of a certain amount of water vapor in the flue gas. As amine solution-based processes, separation processes based on solid adsorbents are cyclic processes where first adsorption of CO2 takes place before the adsorbent needs to be regenerated before it's ready for a new cycle. The regeneration can either be done by changing the temperature of the adsorbent, so-called temperature swing adsorption, TSA, as shown to the left, or by pumping vacuum on the adsorbent, as shown to the right, so-called vacuum swing adsorption, VSA. Also, a combination of the two is possible where both the temperature is increased and vacuum is used, so-called VTSA. The aim is to maximize the working capacity of the adsorbent at the lowest energy requirement as efficient as possible. There are many ways to carry out cyclic separation processes using solid adsorbents. Here are some examples shown. One aim is to minimize the cycle time. In traditional multi-column fixed-bed TSA processes, shown in the top left figure, cycle times are often hours. In order to shorten the cycle time, preferably to a minute or so, new contactor concepts are needed. Moving bed, rotating bed, and fluidized bed concepts can potentially give reductions in TSA and DTSA cycle times, thus reducing the footprint of the separation process significantly. Also, the use of heat pump systems might be important, since it will bring down the need for external heat and then lower the running costs. As previously stated, the main challenges for solid adsorbent-based technologies are twofold. Firstly, reduce the size of the process by being able to carry out fast adsorption-desorption cycles. This also includes finding the right shape of the adsorbent so high gas flows are possible. Secondly, design the process so fast heat and cooling cycles of the adsorbent between the adsorption and desorption steps is possible. These two challenges are certainly connected, and both will reduce the size and heat requirement of the process, and then also the cost. Thank you for listening. If you enjoyed this video and want to learn more about the MOF4AIR project, check our other videos and our website. You can also follow us on social media and subscribe to our newsletter. Thank you for listening.